Good morning everyone. In this lecture I am going to explain about iron carbide equilibrium diagram. Iron carbon system, it is a binary alloy system consisting of iron and carbon. The main constituents of steel or cast iron is iron and carbon. So steel contains about less than 2% carbon and cast iron contains between 2 to 6.67% of cast iron. Before understanding the iron carbide equilibrium system, we have to know the iron allotropy and various micro constituents of iron and steel. Then only we can understand iron carbide equilibrium diagram. Iron allotropy is nothing but iron is in different crystal structures at different temperatures. Okay, it may be a BCC crystal structure or it may have FCC crystal structure at different temperatures. Let us see the cooling curve for pure iron and allotropic forms marked over it. So it is a cooling curve for pure iron. So it is above 1539 degrees Celsius. It is a melting point of iron. Above that temperature, it is in liquid state. And when the temperature is, when it is cooled beyond 1539 degrees Celsius, it solidifies. And first it reaches it has a crystal BCC crystal structure. It is called as delta iron. So when it is cooled beyond 1409 degrees Celsius, it becomes gamma iron. That is, it is having FCC crystal structure and it is non-magnetic. When it is cooled beyond 910 degrees Celsius, it becomes alpha iron. Alpha iron is having BCC crystal structure. When it is cooled beyond 768 degrees Celsius, it becomes alpha iron magnetic. So the non-magnetic properties disappears, non-magnetic properties disappears and magnetic properties will appear. Okay, it is explained here in this slide. Then micro constituents of iron and steel: austenite, ferrite, cementite, pearlite, leadberite. These five are the micro constituents of iron and steel. In the iron carbide equilibrium diagram, these five micro constituents are marked over on the iron carbide equilibrium diagram. So these are very important, and we should know about these five micro constituents. Then only we can plot these different micro constituents on the iron carbide equilibrium diagram. First one, austenite. It is a gamma solid solution. The gamma solid solution is nothing but austenite. It is an interstitial solid solution dissolved in gamma iron. The maximum solubility is 2% at 130 degrees Celsius, and it is 100 times more than that for the ferrite. Next crystal structure, we can see the diagram of austenite crystal structure. So it is a FCC crystal structure. It has more solubility. Carbon solubility in iron is more. Then ferrite. Next crystal structure is ferrite. It is a name given to the alpha solid solution. It is an interstitial solid solution with BCC crystal structure. We know that alpha solid solution is having BCC crystal structure. Maximum solubility is 0.025% at 723 degrees Celsius. At room temperature, it is much lesser, 0.008%. And the limited solubility is due to the shape of BCC structure. So because in the BCC structure, the interstitial positions are very less. So it is very difficult to accommodate the carbon atoms. Even though it is present in low concentrations, carbon significantly influences the mechanical properties of ferrite. Ferrite has a softest structure that appears on the iron carbide equilibrium diagram, and its microstructure is given in the next slide. The ferrite crystal structure, it is a crystalline like crystal structure. So it has the softest structure on the iron carbide diagram. The third micro constituent of iron and steel is cementite. Cementite is nothing but Fe3C. in the iron carbide diagram, so iron carbide represents Fe3C. Fe3 is a iron carbide, and another name for iron carbide is cementite. Cementite contains about 6.67% carbon by weight. It is very hard and it is very brittle because carbon content becomes more, it becomes cast iron. Cast iron is more brittle compared to steel. So it lost its tensile properties and it possesses very high compressive strength. It is the hardest structure that appears on the iron carbide equilibrium diagram. The cementite microstructure is shown below. The cementite microstructure that dots represents iron carbides, Fe3C. The next crystal structure is pearlite. It is a product of austenite decomposition by eutectoid reaction. It is an alternate layers of ferrite and cementite. Okay, it's a combination of ferrite and cementite. Alternate layers of ferrite and cementite becomes the pearlite. So the pearlite structure is shown in this figure. It consists of thin plates of cementite. Thin plates of cementite are given as the lines, inclined straight lines in this diagram. So pearlite is nothing but alternate layers of ferrite and cementite. Then lidubrite, it is a crystal structure consisting of alternate layers of austenite and cementite. It contains about 4.3% carbon. The microstructure of lidubrite is given in this figure. It consists of alternate layers of austenite and cementite. Okay, these 5 microstructures are very useful to draw the iron carbide equilibrium diagram. Next we will go to the iron carbide equilibrium diagram. In this iron carbide equilibrium diagram, it extends up to 6.67% carbon. The compositions between 6.67% and 100% are not shown on the iron carbide equilibrium diagram. So this is an iron carbide equilibrium diagram. In the iron carbide equilibrium diagram, in the x-axis percentage carbon is given and in the y-axis temperature is plotted. So in the x-axis there is percentage carbon 0.8%, 2%, 4.3%, 6.67% carbon is presented. Remaining is iron. So 6.67% carbon, remaining is iron. So this diagram can be plotted into, this can be divided into 2 parts, that is up to 2% it is called as steel, and 2 to 6.67% this diagram is called as cast iron. Okay, so up to 0.8% carbon it is called as hypoeutectoid steel. 0.8 to 2% carbon steels are called as hypereutectoid steels. So 2 to 4.3% it is called as hypoeutectic cast iron. 4.3 to 6.67% cast iron is called as hypereutectic cast iron. In the iron carbide equilibrium diagram, y-axis contains temperature. Temperature 1539 degrees Celsius is the melting point of iron, and 1492 degrees Celsius peritectic reaction occurs. At 723 degrees Celsius eutectoid reaction occurs. At 130 degrees Celsius, that is on the right side, it is plotted on the right side, eutectic reaction occurs. So these 3 variant reactions are occurring on the iron carbon alloy systems: peritectic reaction, eutectoid reaction and eutectic reaction. And you can see different kind of microstructures: austenite, ferrite, pearlite, cementite, lidubrite, and all the microstructures on the iron carbide equilibrium diagram. We have to plot 3 variant reactions as well as the microstructures on the iron carbide equilibrium diagram. Here x-axis contains the percentage of carbon and y-axis contains temperature. The peritectic reaction, liquid plus delta, the solid gives austenite, a solid. Liquid acted upon solid to give solid. On the top left of iron carbide diagram, at 1492 degrees Celsius, the peritectic reaction occurs. That is, at above 1539 degrees Celsius, it is in liquid state. Liquid, it is when acted with delta ion, becomes solid, austenite solid. Below this line, you can see austenite. Below, under the peritectic reaction line, austenite will form. In the iron carbide equilibrium diagram, the three invariant reactions are peritectic reaction, eutectic reaction, and eutectoid reaction. Peritectic reaction occurs at a temperature of 1492 degrees Celsius, and liquid, when acted with solid, gives a solid. It corresponds to 0.18% carbon. An eutectic reaction occurs at a temperature of 1130 degrees Celsius. A liquid gives two solids, solid 1 and solid 2. Solid 1 is austenite, solid 2 is cementite. Eutectic reaction occurs at a temperature of 1130 degrees Celsius, and you can see this on the top right corner, and point E is a eutectic point. It is nearer to U1, W1. So above the point U1, above the point E, it is in liquid state. The iron carbon system is in liquid state. At point E, that is at eutectic point, liquid becomes two solids. Two solids are austenite plus cementite. We know that Lidubrite. Lidubrite is austenite plus cementite, mixture of alternate layers of austenite and cementite. So liquid upon cooling becomes two solids in the eutectic reaction. So in the eutectic reaction, liquid becomes solid 1 and solid 2, and it becomes austenite plus cementite. Austenite and cementite is nothing but Lidubrite. It is an eutectic mixture. It corresponds to 4.3% carbon. The third invariant reaction is eutectoid reaction. It occurs at a temperature of 723 degrees Celsius. In the eutectoid reaction, a solid upon cooling becomes two solids. In the eutectic reaction, liquid upon cooling becomes two solids, whereas in the eutectoid reaction, solid upon cooling becomes two solids. One is ferrite and another one cementite. Ferrite and cementite is nothing but perlite. In the iron carbide equilibrium diagram, corresponding to 723 degrees Celsius, and corresponding to 0.8% carbon, S, the point S, you can see on the 723 line, point S nearer to X4, and this point S is called as a eutectoid point. Eutectoid point, and above that, above the S, it contains austenite. That austenite is converted into perlite. Perlite is a mixture of alternate layers of ferrite and cementite. So one solid becomes two solids in the eutectoid reaction at 723 degrees Celsius and corresponding to 0.8% carbon. Okay, in the eutectoid reaction, one solid becomes two solids, solid 1 and solid 2. In the eutectic reaction, one liquid becomes two solids. In the peritectic reaction, one liquid plus one solid becomes one solid upon cooling. In the iron carbide equilibrium diagram, we are going to study the 6 types of steel. First one is hypoeutectoid steel. On the top of iron carbide equilibrium diagram, X, Y, Z, U, V, W, 6 lines are given, 6 vertical dotted lines are given, and X corresponds to hypoeutectoid steel, Y corresponds to eutectoid steel, Z corresponds to hypereutectoid steel, and U corresponds to hypoeutectic cast iron. V corresponds to eutectic cast iron. W corresponds to hypereutectic cast iron. First consider alloy X. Alloy X corresponds to hypoeutectoid steel and it contains about 0.6% carbon, and in between X and X1 iron carbon system is in liquid state. In between X1 and X2, that is the peritectic reaction occurs and it contains some of the liquid becomes austenite. So liquid plus austenite is present, and when it crosses X2, liquid is completely converted into austenite. In between X1 and X2, liquid plus austenite. When it crosses X2, fully completely it is in between X2 and X3, it completely contains austenite. In between X3 and X4, some of the austenite is an metastable phase and it is not stable above 723 degrees Celsius. Below 723 degrees Celsius, austenite phase does not occur. It is not a permanent phase. So it is converted into some portion of austenite is converted into ferrite and remaining austenite is present. When it crosses X4, it is completely converted into, that austenite is converted into perlite. So at room temperature, it consists of ferrite plus the microstructure consists of ferrite plus perlite. For hypoeutectoid steel, the carbon percentage you can see at the bottom line, it corresponds to 0.6% carbon. It consists of ferrite and perlite structure. So from X to X1 it is in liquid state, X1 to X2 liquid plus austenite, and X2 to X3 completely austenite, and X3 to X4 some portion of austenite is converted into ferrite, and below X4 austenite is converted into perlite. So it consists of ferrite and perlite structure at room temperature. This is hypoeutectoid steel. The second type is eutectic steel. Eutectoid steel. It is marked by alloy Y. In the iron carbide equilibrium diagram, alloy Y is the eutectoid steel. In between Y and Y1, iron carbide system is in liquid state. Between Y1 and Y2, that liquid is partially converted into austenite, and liquid plus austenite is present in between Y1 and Y2. And in between Y2 and S, it is completely converted into liquid. Remaining liquid is completely converted into austenite. Between Y2 and S, the structure is austenite. The austenite is not a stable state. So below S, at point S, eutectoid reaction occurs. The eutectoid reaction, one solid is converted into two solids. That is, it is converted into perlite structure. Perlite is the alternate layers of ferrite and cementite. So at room temperature, it consists of perlite structure. The eutectoid steel contains 0.8% carbon. The third type of alloy is hypereutectoid steel. It is given by the letter alloy Z. In the iron carbide equilibrium diagram, alloy Z is an hypereutectoid steel. In between Z and Z on, it is in liquid state. Upon cooling, some of the liquid becomes austenite and remaining liquid is present up to the temperature around 1100 degrees Celsius. In between Z1 and Z2, liquid plus austenite is present, and Z2 to Z3 completely it is of austenite structure. In between Z3 and Z4, austenite is partially converted into cementite. So below Z4, that is a eutectoid temperature line, the austenite is converted into perlite. So at room temperature, the microstructure will be cementite plus perlite, because the austenite is converted into perlite. So it is a hypereutectoid steel. It contains about 1.4% carbon. So above 2% it is called as cast iron. So hypoeutectic cast iron, eutectic cast iron, hypereutectic cast irons. The fourth alloy is hypoeutectic cast iron. It is given by the letter alloy U. It contains about 3% carbon. In the iron carbide equilibrium diagram, in between U and U1, that iron carbon system is in liquid state. In between U1 and U2, liquid plus arsenate is present. Between U2 and U3, that is arsenate, liquid is converted into ledubrate. Arsenate becomes ledubrate. Arsenate plus ledubrate forms, and between below U3, arsenate is converted into perlite, and perlite plus ledubrate structure will be the microstructure of iron and hypereutectic cast iron, corresponding to 3% carbon. The fifth alloy is eutectic cast iron. The solidification of solidification of alloy V. Alloy V is an eutectic cast iron. It contains about 4.3% carbon. The solidification does not start until point E. In the iron carbide equilibrium diagram, the alloy V, in between V and E, it is in liquid state. E is a eutectic point. Eutectic reaction occurs at a temperature of 1130 degrees Celsius, and liquid upon cooling becomes two solids, that is ledubrate forms. Ledubrate is an alternate layers of austenite plus cementite. So below V1 line, that austenite is converted into perlite plus Fe3C. So at room temperature, it consists of ledubrate structure containing perlite and Fe3C. It corresponds to 4.3% of carbon. The last structure is hypereutectic cast iron. It is a solidification of alloy W. Alloy W is known as hypereutectic cast iron, and it contains about 5.2% carbon. In the iron carbide diagram, W alloy is a hypereutectic cast iron. In between W and W1, alloy is in liquid state. Between W1 and W2, liquid plus cementite precipitates. Between W2 and W3, the remaining liquid is converted into cementite. Cementite remains as it is, and the liquid is converted into austenite plus Fe3C, ledubrate. And below W3 line, that is below W3 line, that austenite is converted into perlite. Perlite plus Fe3C is present. So this corresponds to 5.3% carbon. So we have studied XYZ alloys and UVW alloys on the iron carbide equilibrium diagram. In the examination point of view, iron carbide equilibrium diagram, the figure plus the three invariant reaction and the 6 type of steels have to be explained. In the examination point of view, the microstructures are not essential, because and ion allotropy is also not essential. In order to understand iron carbide equilibrium diagram, ion allotropy and micro constituents of iron and steel are very much essential. It is clearly explained in my book Engineering Metallurgy by Dr.J Aldrin Raj, and it covers entire Anna University syllabus of Tamil Nadu non-metallic materials, and this book is available in online, and it is the publisher is Sri Krishna High Tech Publishing Company, Chennai. Thank you very much.